ever noticed how much statistics there is in the news? The headline announces that the nation's unemployment rate just dropped to 7.4%. Inside, a Gallup poll says that 45% of Americans are afraid to go out at night because of crime. A medical feature reports that taking aspirin may reduce the risk of heart disease by 20%. And back here in the business section, there's a column on new computerized assembly lines and how much they're increasing the quality and productivity in American industry. Not to mention all the statistics here on the sports page. Thanks.
Would you like to order?
Yeah, I'll have 2 eggs over easy and bacon, please.
Okay, thank you.
Numerical facts make up an increasing part of the information that we need in order to understand our world. I call data like these statistics, and there's a branch of mathematics that's also called statistics that helps us to interpret and use these data. But where do the numbers come from? The Gallup poll didn't ask me if I was afraid to go out at night for fear of crime. In fact, Gallup interviewed only 1,555 people. It says so right here at the end of this article. How can information, which is based on such a small number of people, justify conclusions about a much larger group? Thanks.
I'd like bagel.
It's the business of statistics to draw conclusions from partial numerical information and to say how trustworthy those conclusions are. But it's a business not without controversy. The Surgeon General's report on smoking and health says that cigarette smoking is the largest avoidable cause of death and disability in the United States. Most medical experts believe that tobacco accounts for 85 to 90% of the over 95,000 lung cancer deaths in the country each year. But the tobacco industry says that the evidence linking cigarette smoking and lung cancer is weak because it's only statistical. How does statistics arrive at conclusions? And how accurate is statistical evidence? Well, as in any other science, the foundation is accurate observations. In statistics, this means properly collecting the data. If this isn't done correctly, then distorted conclusions are sure to result. Suppose that I wanted to figure out the unemployment rate, for example. I could go to a convenient, busy street, stop people passing by, and ask them if they're employed or not. But would you tell a stranger with a clipboard that you've just been laid off? And how many people with jobs are likely to be out on the street in the middle of the day? Where am I going to find a typical street, whatever that means? And how many typical streets am I going to have to visit before I can get a decent cross-section of the country?
Excuse me, I'm taking a survey. Do you have a job?
Even if I do pick a place and start asking people whether they have jobs, I'm only going to approach people who look harmless. That keeps me safe, but it also means my results are unrepresentative. My survey is biased. The only way to collect accurate data is to follow procedures expressly designed to eliminate bias. The first step is to state carefully what group we want information about. Statisticians call this group the population. For example, if we want to measure unemployment, we have to answer certain questions. What age group are we talking about? What about illegal aliens or people in prisons? Just who is part of the population? In fact, the official unemployment figures are compiled by the Bureau of Labor Statistics. When the Bureau announces the national unemployment rate each month, the population it's measuring is all U.S. residents, citizens or not, 16 years of age or older, who are civilians and not institutionalized. Once the population is defined, the next step is to select a sample, a part of the population from which to draw conclusions about the whole. To measure the unemployment rate, the Bureau of Labor Statistics relies on a sample of 60,000 households.
The household survey is a basic labor force survey which provides us with an enormous amount of data, providing information on the demographic characteristics of people and about their labor force status, their employment, the length of time they're employed, whether they're job seekers, whether they're job losers, whether they're employed part-time or full-time, and so on. That survey is conducted for us on contract by the Bureau of the Census. Interviewers go out to a sample of 60,000 households, which is spread throughout the country in more than 400 areas of the country.
How can we avoid bias in the selection of such a sample? The statistician's answer is to eliminate personal choice by allowing chance to select that sample. Now, these beads are all identical, except for the fact that some of them are light and some of them are dark. Well, let's say I wanted to figure out what percentage of these beads were dark without counting each one individually. And to make things a little bit more interesting, imagine that this box represents working-age Americans, and the dark beads represent those who are unemployed. Now, I've got a scoop here with 50 recesses in it. So if I were to mix up all the beads in this box and then plunge the scoop in, every bead would have the same chance as every other bead of being selected. Moreover, every group of 50 beads would have the same chance as every other group of 50 beads as being taken. Now, that's a subtle point, but it's important. Well, let's try it. Okay, I got 12 dark beads. Now, 12 out of 50 is the same as 24 out of 100, or 24%. So this is an example of a simple random sample. I've drawn a sample of the population, and I've estimated a number, and I'm going to use that number to guess what's going on for the entire population. But what would happen if I did this again? Am I likely to get the same 12 beads? Well, probably not. Oh, I got 8 dark beads. Now, 8 out of 50 is 16%. So I've got two very different numbers. Now, that's a little scary. Does that mean that if I were to take the monthly unemployment survey twice, I'd have to announce two different unemployment rates? It's hardly the basis for sound economic policy. Now, what's going on here is that random sampling has eliminated bias, but it didn't eliminate variability. Now, fortunately, there's a theorem or law in the mathematics of probability that describes this kind of variability when we have several repeated random samples. So while each individual outcome is unpredictable, like the toss of a coin, in the long run, a definite pattern emerges. Now, earlier, I took 30 samples of these beads, and I counted how many dark beads there were in each sample.
My first sample of 50 beads had 12 dark ones, or 24%. The second sample contained 8 dark beads, or 16%, and the third sample had 26% dark beads. Now, after scooping 30 times, I wound up with 8 dark beads, that's 16%, a total of 4 times, as you see on the left. There were 5 samples that each contained 12 dark beads. When I put all my samples together like this, the display looks something like a bar graph. In fact, it's a histogram, a graph that measures frequency. Getting 10 dark beads in a sample, or 20%, happened 6 times, and the histogram shows that frequency. In the same way, you can read the totals that we got before directly off the graph. There appears to be quite a bit of scatter in my results, but most of the samples clustered around 20%, and I know, because I counted them when I put them in, that exactly 20% of the beads in the container are dark ones. Only 6 of my samples contained exactly 20%, but you can see that about 2/3 were pretty close. The results of sampling are usually close to the population truth. Now, the laws of probability enable us to make exact statements about what happens when we have many repetitions of simple random sampling. And what we get is a definite pattern of variability, which allows us to compare the results of the sample with the truth about the population. So how does the Bureau of Labor Statistics get those unemployment figures? Certainly they don't use beads in a box to determine who's going to be interviewed. In fact, random selection is done by a computer. The Census Bureau does this job, first selecting at random a sample of contiguous geographic areas called primary sampling units. Then smaller areas of about 500 inhabitants each, called census enumeration districts, are chosen. Then, again at random, individual households within those districts are chosen. This procedure is a multi-stage probability sample, far removed from drawing beads from a box, but it's still a random sample, and the use of chance eliminates bias in choosing who's to be interviewed.
Right. How many hours did you work last week at all jobs?
Around 35, 37, somewhere in there.
Did you lose any time?
Census Bureau interviewers visit approximately 60,000 households each month. At home with a trained interviewer, people speak more freely. Although participation isn't required by law, over 95% of those contacted agree to be interviewed. A number of questions determine if each person is in the labor force. The survey also collects other important social and economic data.
What was the most important activities or duties on your job?
Teaching English. That's what I teach.
But just as with our beads, the variability of the sample doesn't disappear even with the most careful choice of the sample.
But the mathematics of probability enables the Bureau of Labor Statistics to state pretty accurately what that variability is and what the margins of error are within which most of the sample results are bound to fall.
Everyone, but everyone, wants to live in a world of certainty. Even the statistician wants to live in a world of certainty. I think that our job is to explain to people that there is no such thing as absolute certainty, and that what we can do is to provide a set of statistics which have some error surrounding them, something that we often call sampling error or variance, which will tell them what the basic tolerances are. The unemployment rate, for example, if it moves by 1/10 of a point, we in the Bureau of Labor Statistics and all our releases and everything we say will say that it was about the same. If it goes up or down 2/10 of a point, this is the overall rate, we will say that there has been a change.
Let's take another look at the arguments linking cigarette smoking and lung cancer. And let's see how confident we can be about the statements that are made there. Now, several major medical studies have shown a very strong connection between cigarette smoking and the incidence of lung cancer. Smokers are more likely, 20 times more likely in one study than non-smokers, to get the disease. Now, such a strong correlation is very unlikely to be due to chance alone. But can we actually say from just looking at these samples that cigarette smoking causes lung cancer? I mean, isn't it possible that some third factor might be involved? For example, it could be that cigarette smokers have a genetic predisposition to both nicotine addiction and lung cancer. If that was the case, we'd still see this strong connection even if cigarette smoke had no effect on the lungs whatsoever. In order to prove a cause and effect relationship, we have to conduct an experiment. Now, for example, we could take two groups of children and require one group to smoke 2 packs of cigarettes for every day of their life, while not allowing the other group so much as a single puff. Then, if the groups had been selected at random, any difference in the incidence of lung cancer could be confidently attributed to smoking cigarettes. But that's an experiment that we couldn't do for ethical reasons, although it's really no different in design from the way medical experiments are conducted all the time. Randomized comparative experiments are the mainstay of research in medicine and in agriculture and in many other fields. These experiments are comparative because one group takes an experimental treatment, while a second or control group is given an alternative treatment. And the subjects are assigned to these groups at random in order to eliminate bias and to ensure that the groups are comparable when the experiment begins. Now, in medicine, a randomized experiment is called a randomized clinical trial. One of the largest such trials ever undertaken is the Physician's Health Study, which is investigating the effects of taking aspirin on reducing heart disease, and in the same study investigating the effects of taking beta-carotene, which is a form of vitamin A, on prevention of cancer. Now, cardiovascular disease and cancer are responsible for 2/3 of the deaths in the United States each year, so work on their prevention is one of the most important challenges facing epidemiology, the study of disease.
What is it about what we do, what we eat, what our environment is, what our occupations are, something about our history, our medical history, our family history, that leads one group of people to be more or less likely to develop a disease than another group of people? And it's these factors that we're trying to identify. We go at it from a couple different ways. One is what's called descriptive epidemiology, looking at the trends of diseases over time, trends of diseases in one population relative to another population. We don't interfere in the process, we just observe it. But the second type of epidemiology, which is, as an example, the Physician's Health Study, is experimental epidemiology, experimental study, an intervention study, where we take a group of people who have the treatment, who are exposed to the treatment, a group of people who aren't. But the difference is that we, the investigators, determine who will be in what treatment group, who will receive the treatment and the placebo, who will be exposed and who won't be exposed.
We would hope to either provide firm medical evidence on which public policy can be based with regard to aspirin and beta-carotene, or alternatively, if in fact we find no association between these treatments and the outcomes under study, then we could safely permit the rechanneling of existing funds to other areas of research rather than providing inconclusive results that really leave us in a quandary as to whether or not there really is or is not something going on here.
The Physician's Health Study is an experiment because the effects of certain treatments, such as taking aspirin or beta-carotene, is being compared with the effects of identical-looking but inactive pills called placebos. And it's a randomized experiment or a randomized clinical trial because who gets which kinds of pills is determined by random assignment. Here's the design of the study.
Almost 22,000 physicians agreed to participate. Although the random assignments were actually made all at once by a computer, you can think of the design this way. First, half of the physicians are randomly selected to receive aspirin or placebo aspirin. Then each of these groups are further split into beta-carotene and beta-carotene placebo groups. That makes 4 experimental conditions: aspirin and beta-carotene, aspirin and a placebo and beta-carotene, and 2 placebos. All 4 groups, of course the doctors don't know what group they're in because of the placebos, fill out reports on their health every 6 months and mail them into the Physician's Health Study. There the reports are coded by staff members who also don't know what groups the doctors have been assigned to.
One of the things that you want to make sure of is that the information that you're obtaining on those who are in one treatment group and those that are in another treatment group, that information is identical. And one of the ways to do it is to ensure that the people who are gathering that information don't have knowledge of what disease the person may have or what treatment group they've been assigned to. And that's called blindness. When the interviewers or the people that are gathering the information don't have knowledge of the treatment group. Now that's just one half of it. The other half would be the people who are receiving the treatments. If they also don't have knowledge of what treatment group they've been assigned to, that's the second part of blindness, or double blind.
Now, taking aspirin or vitamin A doesn't entail the same kinds of risks as smoking cigarettes, but there are some possible harmful side effects. So we really have to ask ourselves whether any experiment which involves drugs is ever ethical, especially one in which the subjects don't even know whether they're getting the drugs or not. Now, it's true that all of the doctors in the study gave their informed consent, but I asked Dr. Hennikins what circumstances he felt justified a clinical trial.
I'm certainly aware of the fact that there are instances where it would not be ethical to do a randomized trial. Certainly when penicillin was introduced for the treatment of pneumococcal pneumonia, which was virtually 100% fatal before the introduction of this agent, and then after the introduction, the mortality rate plummeted significantly, I think it would have been unethical to do a randomized trial to withhold that sort of treatment from people who might otherwise need it. But even in the United States today, in the 1980s, I think there's a delicate balance between when to do and not do a randomized trial. I think on the one hand, there must be sufficient belief in the agent's potential to justify exposing half the subjects to it, and I think there must be sufficient doubt about its efficacy to justify withholding it from the other half of subjects who might be assigned to the pills with the inert ingredients or the placebos.
Despite the possible risks, almost all 22,000 physicians continue to take the drugs and send in their reports. Why does the study need such a large sample?
What we are concerned about in any study is getting to the end of 3, 4, 5 years and seeing that there's really no difference between the treatment groups. And what we don't know is whether there's no difference because there really isn't one, or whether we're not seeing a difference because our sample size wasn't large enough to pick it up. What's called a null result, seeing no difference, but an uninformative null result because we don't know why.
Let's be very careful here. Any significant difference between these groups is almost certainly due to the drugs. That's because the random assignment of the subjects to the different treatment groups helped to ensure that they were comparable before the experiment began. Now, what do I mean by significant difference? I mean a difference that's larger than that which we might expect due to chance alone. So chance arises here in two different ways. First, we make deliberate use of chance in order to eliminate the factors that might cause bias. Then we use the laws of probability to compare our results to what we might expect just from chance alone. This enables us to see if our findings are meaningful. Now, these concepts are essential in what statisticians mean by proper collection of data. Random sampling and random assignment are two ways for eliminating bias. Sampling, looking at a part of a large population, and assignment, allocating subjects to different treatment groups in an experiment, both make use of the key idea of deliberately introducing chance. The distinction is that in an experiment, we can take control of the relevant behavior. We can even, like the directors of the Physician's Health Study, get the participants to agree not to take any other aspirin or vitamin A except for what they might be receiving in those pills that they get in the mail, and to control for other factors that might or might not be relevant, like nutrition. We depend on the washing out effect of the large sample size and the random assignment to groups. Now, just as with our earlier examples, these beads and the unemployment figures, the larger the sample size, the less likely our results are to be due to chance alone. If we want to observe a specific effect, like a 20% reduction in cardiovascular disease due to taking aspirin, then a larger sample size means that we're more likely to see the effect, and also it means that we'll be more confident that our results are not due only to chance. In other words, it means that our experiment is real and repeatable. That's one of the reasons why the Physician's Health Study enrolled 22,000 doctor participants. But does a randomized experiment always require such a large sample size? Well, that depends on a lot of factors. If we think we know what all the variables are, then there's some really lovely mathematical techniques which can help us reduce the sample size and hence the cost of the experimentation. Let me show you what I mean.
Today's cars do things yesterday's cars didn't.
Motor oils often advertise that they reduce your gasoline consumption. But we know that other factors also affect mileage. The type of car makes a difference, and so does driving style.
Exceeding recommended RPM.
If we want to test the performance of 4 motor oils, we'll need to use some different cars and some different drivers. The mechanics of the test are pretty straightforward. We give each car the same precisely measured amount of gasoline.
50 exact milliliters. Yes, indeed. 50 milliliters.
And then each one gets a different oil.
A, B, C, D.
The test is almost ready to begin. But let's look more closely at what's going on here. 4 cars and 4 drivers make 16 car-driver combinations. To test all 4 oils, you might expect that 4 times 16, or 64 test drives, would be necessary. But here's where we can get clever in the design of this experiment. If we arrange the cars and drivers in a square, then we can assign the 4 oils in a particular way. Notice that each oil is used just once in each column and once in each row. This arrangement is called a Latin square. The beauty of the Latin square design is that each oil is used with every car and with every driver. That way, we can use both logic and calculation to draw conclusions about the performance of the oils over the full range of cars and drivers. We're still making use of randomization in our experimental design. The key to the success of the Latin square is to assign the 4 drivers at random to the columns, the 4 cars at random to the rows, and the 4 oils at random to the letters A, B, C, and D. During each round of driving, the speed is clocked, and the distance each car reaches is measured. Once the first round of tests has been completed, the drivers are rotated to different cars. When all 16 drives, remember 16, not 64, have been conducted, the Latin square design allows us to determine the performance of the oils separately from the effects of car type and driving style. Remember, what we're really after here is a comparison of the effects of the different motor oils on gasoline consumption without getting confused by the different kinds of cars and different kinds of drivers. Now, in a more complicated case, like cardiovascular disease or cancer, we don't even know what those confounding factors might be. So while a Latin square design might be economical, it's not always applicable. Deciding what is applicable and appropriate is one of the statistician's most important jobs. Whatever we want information about in the whole wide world of the physical sciences or the social sciences, accurate data collection is more than just a series of correct techniques. Now, it's crucial that we have accurate measurements, but we have to know what we want to measure, why we want to measure it, and we have to be able to do something with those measurements once we get them. Now, next time, we're going to look at ways of organizing data that make their meaning immediately apparent. We'll see how to convert often confusing arrays of numbers into striking visual images.